Dalton's law of partial pressure states that the total pressure of a mixture of gases is equal to the sum of the partial pressures of the individual components at constant temperature and constant pressure. So what this is saying is that if you have helium gas in one container and you've got 2.41 atmospheres of helium, and you have oxygen gas in a container, and let's say you have 1.42 atmospheres of oxygen, and they're both at a certain temperature and a certain pressure. If you combine these two gases and keep them at the same temperature and the same pressure, then their total pressure, P total, would just be the sum of these individual pressures, which is 3.83 atmospheres. Okay, if you combine the gases. Now, what you would have in this 3.83 atmospheres, you still have that the partial pressure of helium is 2.41 and the partial pressure of oxygen is 1.42. But the total pressure of that system would be the sum of those together. Dalton's law can be shown mathematically. You would say that the total pressure would be equal to the pressure of gas A plus the pressure of gas B plus no matter how many gases that you had in that container, just the sum of their pressures. Sometimes you're not given the flat pressure of the gas, pressure of A, pressure of B, etc. Sometimes you're given the amount of the gases and at a certain temperature and pressure. So the equation can also be written that the total pressure is equal to the sum of the moles, however many moles, times RT divided by V. And that's just a variation of PV equals nRT, summing up the moles. So let's apply this concept to this problem. Calculate the total pressure at 3.2, it's not atmospheres, is it? Because we're calculating the pressure at 3.2 liters and 298 Kelvin in a gas mixture that is 6.2 times 10 to the minus 3 moles of oxygen and 4.17 times 10 to the minus 4 moles of neon. Okay, so the total pressure is going to be the sum of the moles. So I'm going to take 6.2 times 10 to the minus 3 and add that with the 4.17 times 10 to the minus 4, and I have that the total moles is 6.62 times 10 to the minus 3 moles times R, which is 0.0821 liters atmosphere per mole times Kelvin, times my temperature, which is 298 Kelvin, and that is all divided by a volume of 3.20 liters. And I would have that the total pressure here is 5.06 times 10 to the minus 2 atmospheres, which can also, of course, be reported as 0.0506 atmospheres. They're the same number. They're both a correct answer. Okay, another variation of a Dalton's law problem is to use this formula, that the partial pressure of some individual gas is equal to the mole fraction of that gas times the total. So let me tell you what a mole fraction is. A mole fraction is like a percent, okay? And the little I, it just stands for some individual gas. You can make it an A, B, C, whatever. But it's like a percent. So the mole fraction of some gas, whatever it is equal to the moles of that individual gas and it's divided by the total moles of all gases and that's a mole fraction. You just don't multiply it by 100%. So do you see that the concept of mole fraction, it's like a percent, but you aren't multiplying it by 100%. So let's have a variation of the previous problem. And that, let's say that the total pressure is, let's look back and see what it was, 0.0506 atmospheres in a mixture of 6.20 times 10 to the minus 3 moles of oxygen and 4.17 times 10 to the minus 4 moles of helium. Let's calculate the partial pressure of helium. Okay, we're going to calculate the partial pressure of helium. In this equation, we're going to have to use this formula because the problem doesn't give us a volume and temperature, so we can't use PV equals nRT. To calculate the mole fraction, we're going to take the moles of helium, the 4.17 times 10 to the minus 4, and we're going to divide it by the total of the 2 moles, the 6.2 times 10 to the minus 3 plus the 4.17 times 10 to the minus 4. That will give us the mole fraction for helium. Okay, and I've already calculated that. The mole fraction for helium is 6.30 times 10 to the minus 2. And mole fractions, I didn't say this earlier, they're unitless because you take moles and divide it by moles. So there's no units on a mole fraction. And I'm going to multiply that by the total pressure. And that will show me that the partial pressure for helium is 3.19 times 10 to the minus 3 atmospheres. And now I could work the partial pressure for oxygen the same way, plugging in here the partial pressure for oxygen instead of helium. Or I know the total pressure is 0.506, and now I know the partial pressure of helium. I could likewise subtract these two numbers and find that the partial pressure of oxygen is 4.74 times 10 to the minus 2 atmospheres. Either way would give me the same correct answer.